So in terms of noise, which noises are we talking about? So today the focus is on noise. And on noise, we're going to be talking about thermal noise. We're going to be talking about shot noise. And we're going to be talking about amplified spontaneous emission. These are all additive noises, and in fact these three will be modeled universally as additive white Gaussian noise. So that's one of our first simplifying assumptions. However, it's a very good assumption for most of the regimes of interest in typical optical communication systems. So the thermal noise let's say the thermal noise is very common in all systems. All systems using electrical detection have thermal noise. So any detection circuit is going to be characterized having thermal noise, so this is very similar to what we see in any classical digital communication source. Shot noise is found in various communication systems, but most importantly for optical communication systems, it comes from PIN photodetector. So these two sources of noise, both the thermal noise and the shot noise, are characteristics of photodetectors. We'll be focusing on the PIN. We won't be looking at APN. You can certainly find out theory about these and others, but the basic concepts are the same and the simulation aspects are similar, so we'll be just focusing on the PIN. Amplified spontaneous emission is created during when using optical amplifiers. Almost all systems involve some form of optical amplification, whether it's by using an EDFA, an erbium doped fiber amplifier, or using an SOA, a semiconductor optical amplifier. Both of these devices will be introducing a form of noise which is very wideband. It's called ASE noise, or amplified spontaneous emission. So that will be the focus of today's lecture. And we'd like to know how we can characterize these noises and use them to create a theoretical prediction of the bit error rate. Of course, there are other noise sources which we will not be talking about today. So not up for discussion today would be like crosstalk, which is interference across channels. For sure we'll be talking about filtering effects, and the reasons that we have filtering effects is trying to avoid crosstalk. So although we won't be characterizing it, we will be discussing issues related to crosstalk. There's also I'll say intersymbol interference, which we can think of as I guess we can think of it as a noise source, we can think of it as a distortion, but I'd like to think of it as a noise source. So these two issues are related to filtering. And so although we're not going to be predicting BER based on the level of crosstalk, although there's certainly results for that, what we're going to be focusing on is filtering, and that filtering is used to avoid these. So I'll introduce the topic on Thursday with some discussion about when intersymbol interference comes in, what are typical ways of avoiding it, and so on Thursday, when we get to the second half on filtering, we'll be talking a little bit about pulse shaping, and ISI avoidance. And pulse shaping can also be used to reduce crosstalk to allow tightly spaced channels. So they're all interrelated. So those are the big lines of what we'll be covering this week.